Yo, what's up? It's your boy, Mr. AC. And what I got for you guys today is our very first episode of school coming back, and we are talking about exponential functions. Now, some of you, this might be a little review. For others, this might be brand stinking new. So let's go ahead and dive into our very first lesson now. So make sure to check your email and be in the Google Classroom. With that being said, hopefully you checked that and you got that good to go, because you're gonna take these notes and you're gonna do the practice problems on the Desmos. But anyways, let us go ahead and get rolling, y'all, because y'all know we are here to learn. We cannot let this take us down. Let's get rolling. We are in our very first lesson of exponential functions. What is an exponential function? Well, I'm going to show you through a little demonstration of this problem here as a good little review. What does this function to the left remind you of? Hopefully this is going to remind you of linear functions. It's a straight line. So if you look over here, 0 comma, well, right here is 2, so 0 comma 2. At 1 it's 7, so 1 comma, we'll put 7. At 2 it is 12, so then it is 12 right here. And then at 3 it is 17. Notice how we grow constantly. We grow at the same rate. We go up 1 2 3 4 5 over 1, up 5 over 1, and you would do that no matter what. You notice that this growth is constant, linear. It's growing by the same amount. Let's go to this other graph that has this kind of wicked curve, right? You can see this curve, it starts off very slowly and then it starts to take off. We spoke about that previously. Let's go ahead and graph this. 0 comma 2. So look, they both have the same starting value, but you'll notice something dramatic is going to occur. 1 comma 6, 2 comma 18, and I can't even see 3. So I'm pretty much already like, holy crud, that's all I can get to. Well, that's okay. Let's write an equation, right? So maybe this will help us and make us understand, well, what's the pattern to the left here? This is what we call linear. Well, if you look at the pattern here, you started with 2, so I'm gonna write y equals 2. And what's happening every time you go down this table? Well, if you look, we are adding by every single time. Doesn't matter what, we're adding by what? Well, we're adding by 5. Boom, boom, boom. Well, check this out, y'all. Check this out. 2 plus 5 is 7. 7 plus 5 is 12. 12 plus 5 is 17. So 17 plus 5, 18, 19, 20, 21, 22. Bazam, shazam, we got that down. Y'all know what I mean? Let's go on to exponential functions. What are exponential functions? Well, if you look here, this one's a little bit tough because we don't just add by. Well, if you look here, right, maybe you want to write, let's add by 4. Well, 2 plus 4 is 6, but 6 plus 4 is 10. It is not 18. So this graph to the right is not linear. It's something else. Well, this graph to the right, my friends, if you have not seen, and plus the video is called Introduction, it is what we call exponential functions. This is an exponential graph. What does that mean exactly? Good question. You know, what does it really mean? Well, what exponential functions are functions that grow with constant multiplication or constant division. So now instead of thinking, what are we adding by every time? Why don't we ask ourselves, are we multiplying by something every time? Well, let's take a look. Well, 2 times what will give me 6? Well, 3. 2 times 3 is 6. What's 6 times 3? 18. 18 times 3. Let me take out my phone. 54. So you can see why we couldn't even fit this on this graph. I mean, look how much it's growing by. It's shooting up like crazy, and we can't get to 55 on this graph. So if you look here, things that are constantly multiplying by a number, where it's repeated multiplication, is exponential. When we have repeated addition, it is linear. So if I was to write the equation over here, let's finish it. This would be 2. Well, what's my pattern? Well, I'm adding by 5. So 2 plus 5x, like this. Well, what is the situation here? Well, to give you the equation, we're going to start off and write y equals 2. Well, what are we doing every time? Well, we're multiplying by 3 every time. But now, where does the x go? Because the x does not go over here. It's actually going to go somewhere else. Well, let's go ahead and take a look at this, right? For example, if I write 2 times 3, that's going to give me 6, right? 2 times 3 gave me the 6. Well, let me write 2 times 3, right? That was what we started with. 2 times 3 is 6, and then we multiplied by another 3. So you can see I have a repeated 3, and that's going to give me the 18. Well, how else can I write this? Well, I can write this as 2 parentheses 3 to the power of 2. And watch how this is the same thing. What's 3 squared? 3 times 3 is 9. 9 times 2 is 18. And you can see we're going to match this right here. So if you look, every time we repeat a number with multiplication or division, it's going to have this to the power of 2 or 3 or 4, however many times you want to keep going to fill the rest of this table out. So if I was to write my x, well, my x doesn't go next to the number, it's actually going to go on the exponent. So this right here would actually be the equation for this graph right here. So hopefully you can see the big difference between the two. So let's go ahead and define a few things together. So let's take a look at what this is right here. Exponential functions can be rewritten as y equals a b to the x. Notice how it was very similar. Well, what does the a represent? Well, the a represents, let me go ahead and write it. The a represents the starting value. So if you think about it, this number in front is always your starting value. That is very similar to over here, how this 2 was the starting value in this function. So if I was to write this general form here, a represents the starting value. Well, what does the b represent? Well, b is your constant multiplier. It is a number that you are constantly multiplying by or dividing by, depending on your problem. A represents the starting value, b represents the constant multiplier. And that's what exponential functions mean. Y is your output and x is your input. So just so you know, that's exactly what those values mean. So hopefully we got an idea of exponential functions, a little bit of how it goes from graph to table to equation, and a little bit of how it kind of forms. In this next segment, we're going to install or introduce some new vocabulary, something that is called growth and decay, and the best way to do it is for us to do some graphing. So let's take a look at this question here. Explain what each component of the function is and graph it. Is this function growth or decay? And we're going to start to learn something called a growth factor and something that is called a decay factor. And it's actually something that we covered, but we just haven't defined it just yet. Now I have my little handy dandy calculator with me. So when I say explain what each component of the function is, I forgot to put is, we're talking about what does the 3 mean and what is the 2. Let's go ahead and graph this and then you'll see what I'm talking about, because if we graph this and we fill out the table, I think it'll make all the sense in the world. So let's go ahead, we'll start with -1. It's always good to get a few points along the way. So I'm gonna hit 3 parentheses 2 raised to the power of -1, right? That way I can plug it in. If you're curious, later on we're gonna learn what it means when you raise something to the -1. Right now, you probably gotta use your calculator. We get 1.5, so I'm gonna come over here, write it down 1.5 like this. So let me go ahead and go -1, 1.5. Now I went by 5s on this graph. The y values go by 5, just so I can fit this graph a little bit better, but just know it's okay to estimate it a little bit. So we know at -1, my x value, my y value is 1.5. So I'm gonna come up here, and I'm gonna go ahead and mark it here. I'm gonna say roughly 1.5 right there. It doesn't have to be perfect, all right? It doesn't really have to be perfect. Let's plug in 0. Now we're gonna do the same thing. 3 hit 2 raised to the power of 0. And voila, we get 3. Right there, bazam. So I'm gonna go to 0, 3. So I'm gonna mark it right here, 0, 3. And guess what? Well, we talked about this prior. Whenever your x is 0, this is your starting value. So I can actually come over here and say, hey, the 3 is the starting value. That's what the 3 represents in this problem. This is your initial value. So even before you started, you could have just saw the 3 and noticed, okay, at 3, my starting value is 3. Now I said that kind of weird. All right, let's plug in the rest. Again, you can use your calculator or you might be able to figure out a little pattern along the way here. So we're gonna raise this to the power of 1. We get 6 here. The color change, no big deal. 3 raised 2 to the power of 2. That's the power of 2 right there. That is 12. And I'm gonna pause here for a moment because I want you to notice something that I'm noticing here. Obviously the 1.5 was a little bit tricky, but what is the pattern happening down in this table? Well, if you look from here, we are multiplying by 2. 3 times 2 is 6. 6 times 2 is 12. So 12 times 2, we get 24. Now, obviously, I have to use the equation to be able to plug in 10, right? And I expect 10 to be pretty big. 3 raised to the power of 10, we get 3074. The 2, if you notice, that's why the x is on the exponent. Whenever the x is on the exponent, right, that means we're repeating 2. Well, what's in between the 3 and the 2 is multiplication. So when I say we're repeating 2, I can come out here and say the 2 is the constant multiplier. We are constantly multiplying by 2. In other words, let me introduce a new language now. We call this the growth factor. This has a growth factor of 2. Now, why is it growth factor? Well, look on the table. Are my values growing as we go down, or are they getting smaller? Well, they're getting larger, so it's gotta be growth. So that's why we call it a growth factor like this. Now, if I was to go and sketch this now, let's take a look at how it looks like. We'll do 1, 6 here, 1, 6, and again, it's not gonna be perfect. I'll put it right here. 2, 12, I'll put it right here. 3, 24, which is somewhere over here. Bam. So if you look at this graph, it's gonna look something like this. And if you notice, like we talked about, it's not a straight line. It is exponential. It's kind of curved, and then this would go down this way if you follow the pattern. So there would be my graph of my function. And something that's really important to note here, if I was to keep going, I'm running out of space, right? At 10, it's at 3074. It's gonna keep going up, and that's because we're just multiplying by 2. Everything is doubling. So double 24, 48. You double that, you double that, you double that. And at some point it's going to shoot up and increase like crazy. So in this problem, this function represents growth because our y values are increasing. So the function is growth and the y values are increasing. Our growth factor would be 2, same as constant multiplier. Awesome. And you can see how the graph from left to right, because we always read graphs from left to right, you can see how it's shooting up. So it is a growth. This function is growth. It is not decay. Awesome, awesome, awesome. Let's go ahead and go on to something that we consider decay now, so that you get an example of both. Let's take a look at this problem here. Now again, to do -1, I'm gonna need the calculator for this one here, but now we're gonna try to do this without using the calculator too much, but you can if you want to. We get 60, and that looks weird. Again, maybe if you are really understanding this, a challenge for you is to understand what does it mean when you put negative numbers in the exponent. Well, I want you to look at this equation up here. Well, now I want you to think about for a moment, what does the 30 represent? Well, the 30 is your starting value. So 30 is the starting value. That also, our starting value will always occur when your x value is 0. It's kind of like the y-intercept, if you would say. So then we know right here to just start it off, we can put 30 right here immediately. And I'm gonna go to the graph, hit 0, and I'm gonna mark it 30 right there. This is my starting value. Now, what's happening? Well, in between these two, we are multiplying. What are we multiplying by? Well, we're multiplying by 0.5. This 0.5 is our constant multiplier. Well, is it decay or is it growth? Well, we're gonna see what happens when we multiply by 0.5. What's 30 times 0.5? You can use your calculator. That's 15. Well, if you actually look now, this actually means our function, if we're multiplying by 0.5, means it's getting cut in half. We are taking that value and we're just gonna keep half of it. Well, I might go to my equation now, and I might just do 15 times 0.5, and that's gonna give me 7.5. So 7.5, boom. And then I will do the same thing right here, 7.5 times 0.5, and that gives me 3.75. So 3.75 right here. And then obviously I had to use the calculator for this one. Obviously I wanted to show you two different ways we could do it. One with the equation, one with just the patterns. But let's go ahead and plug this one in, because we know this one, I don't want to do this and go all the way down till 10. So 30.5 raised to the power of 10, and we get 0.0292. 0.0292. So let's go ahead and sketch this and see how this is looking like now. Well, there it is, -160. That's like way up here, y'all. It's out of our freaking image, right? So with that one, we can't even sketch. So we'll just know that this is going like up like this. 1,15. Nice. This one's hitting the graph really nicely, and I'll keep it the same color. Why not? Boom. At 2, it is 7.5. I do have to approximate this. I'll say maybe somewhere here-ish. At 3, it's 3.75. So again, I'm going to estimate it. Again, this is 3. The y value is 3.75. So somewhere here, 3.75. This would be 7.5 right here. And then this right here, 15, which you got. And then at 10, which I don't even have on the graph, it's like at 10, this is 8, 9, 10. Let's say it's like, it's even lower than that actually. It's like right here. It's almost close to 0, right? So you can see this graph. Look how it looks like when we look at it from left to right. Boom. So when we read this graph from left to right, you're going to notice the y values are going down and they're decreasing. You can see they're kind of decreasing a little bit, curvature, but then bam, at some point you can see that it's just going to get smaller and smaller because we keep taking half of it. So if you look at this graph is going downward like this. So that tells me right away, okay, this graph is decay because the y values are decreasing here. So you'll notice our y values are decreasing, and then you can kind of see how it looks like on the graph, right? This is really just hitting on the heart of exponential functions, and hopefully you got an idea of how it looks like on an equation, a table, and a graph. With that being said, the Algebra 2 team would like to say I hope you're doing well. We'll see you for episode 2 next week.